All right, guys, we are now looking at a concept dealing with functions called the average rate of change. The questions usually are posed this way. On a function f of x, find the average rate of change over the interval a to b. Now, it's easiest to explain this first from a graphical perspective. Long and short of it is, okay, when you're asked to find the average rate of change on a function f of x from a to b, that means quite simply this. You're finding the slope of this blue line. You're finding the slope of this blue line. And of course, the slope formula is y2 minus y1 over x2 minus x1. You know that well. However, let's look at it in function perspective. The interval a to b are 2 points on the x-axis, a to b. They're the 2 strikes. That's the interval along the x-axis, okay? The corresponding point moving up to the function means evaluate the said function, x, f of x, at a. So this point should be a f of a. This point, resulting from a vertical line up to the function, should be b f of b. And therefore, the slope of that line, or in function notation, noted as the average rate of change, is the difference in the y's over the differences in the x. So that's f of b minus f of a over b minus a. Let's state that again. Average rate of change is the slope of a line connecting 2 points on a function. Typically stated in this format, find the average rate of change on the function f of x on a given interval a to b. Okay? The interval implies from some x value of a to another x value of b, which implies from the slope of the line from point A, f of a, to point B, f of b. Average change, average rate of change, indicated as the ARC, as we see, is given by this formula, none different than what we found before. An example. Find the average rate of change for the function f of x equals x squared on the interval 2 to 4. Here's my graph of the function y equals x squared. My interval is along x values from 2 to 4, okay, which means the corresponding y coordinates, the function x squared evaluated at 2 is 4, therefore this point is 2, 4. Function evaluated at 4 is 16. The slope of the blue line is the average rate of change, which is the difference in y's over the differences in x. So that's quite simply 16 minus 4 over 4 minus 2, which, as you see, simplifies to 6. Remember that, because we're going to come back to that in a slightly different fashion momentarily. Take another function. This is a function that maps the position of an object thrown straight upward. Thanks to Isaac Newton, we know the position function as a matter of time. And this is governed by gravity and the object speed. If you're in physics, you'll know and appreciate that. Nonetheless, you can still appreciate from the mathematical standpoint what the average rate of change is going to be, okay? Time is measured in seconds and distance is above the ground in feet, okay? All right, so you throw it up, gravity will pull it back down, depending on how with what initial velocity you give it will determine how high it goes. All right, we have the graph as shown. We're going to ask you to find the average velocity. And you say, well, I thought average rate of change is what we're doing. Well, for this application, the change in position per unit of time is what is called velocity. And the change in position over a given period of time of 3 seconds is going to be called the average velocity. So it is just a specialized application of the average rate of change. The protocol, procedure for solving it, none different. Find the average rate of change on the interval 0 to 3, meaning find the slope of this blue line. That's what it means. Find the slope of that blue line over this interval along the bottom axis, which this time represents time, from 0 to 3 seconds. Okay? So, the corresponding points, this is my A, my F of A is 0, or should I say S of 0 is 0. My function evaluated at 3, I'll leave that for you to compute to be 240. Therefore, the average rate of change, or particular to this problem, the average velocity, 240 minus 0 over 3 minus 0, 80, which in terms of our velocity is measured as feet per second. Okay? 80 feet per second is the average velocity of this object in the first 3 seconds it is released from ground level. Okay? Okay, we're coming back. We're going to take a more abstract look at what we've done. I should say more of a generalized as opposed to abstract. Okay? So we're going to use our formula, which we know, f of b minus f of a over b minus a. More generally, that is, instead of putting numbers in on the interval, we're just leaving it a to b, which implies, okay, the function evaluated at b minus the function evaluated at a. Well, the function is simply x squared, so the function evaluated at b is b squared. The function evaluated at a is a squared over b minus a. This naturally lends itself to wanting to factor, resulting in cancellation of b minus a, resulting in a final of b plus a. Okay? Let's take the results we found previously. We were asked to find the average rate of change on x squared from 2 to 4. That was found to be 6. Well, guess what? No different here. The interval, 2 to 4. That's a, that's b, b plus a is 6. Okay? Now, in that case, we should be able to determine the average rate of change for x squared on any interval. Okay? On any interval. Not just 2 to 4, 1 to 3, 2 to 12, what have you. Okay? Typically, we want to use that on an interval no matter how large or how small. Okay? And more often than not, we want to keep that on a small interval. That's usually why we do the generalization. Okay? So if we were to say, let's take a look at that ARC on this interval 2 to 2.01, okay? All we need to do is go back, plug in B as 2.01, plug in A as 2, giving us 4.01 as the average rate of change on this instance, and 4.001 on this guy, okay? So the generalized approach is much preferred when you have a smaller interval or when you're doing more than one interval. Nonetheless, the generalized approach is typically how you would expect to derive things in mathematics. All right, so let's take a look. We're going back. We're going to do the generalized approach on this, our object thrown upward and governed by this function, thanks to Newton. Okay, the definition: FB minus FA, B minus A. The function evaluation of f of B minus the function evaluation f of A is as it is reported here. B is replacing T. A is replacing T. Okay? It's all he's doing is substituting that back in, putting it into the form, and now we're going to do the algebra. Invariably, the algebra wants to rid ourselves of the denominator, B minus A, so we want to shuffle and factor expressions in the numerator in an effort to bring about that cancellation. So follow what we do here. Okay, the first order business there was just to distribute that negative sign. Okay, distribute that negative sign. Okay, then I can easily see that all the terms in the numerator are divisible by 16, and therefore I'm going to pull out the negative 16 as a common factor, resulting in this. Okay, this is then going to be factored via grouping, okay, or factored in the sense I'm going to show you here. Okay, the b squared minus a squared is b minus a and b plus a. Okay, this expression, the 8 can come out, and we have the b minus a. Now, both of these the numerator contains this 2-term b minus a, which can be pulled out as a common factor here. Agreed. You have to watch your algebra, okay, affording us this cancellation, okay, between the b minus a and the numerator and denominator, okay? And this is what we have. This is the very generalized expression for the average rate of change. Now, you'll recall previously that we found the average rate of change on that 0 to 3 seconds was equal to 80. Well, plugging in B as 3 and A as 0 in here would yield the same thing. But, okay, more importantly, a lot of times we want to shrink that interval down, okay? And when we shrink that interval down, say going from 2 to 2.01 seconds, that's a span of only 1/100th of a second. And what we do is we move from finding the average rate of change, or as particular to this problem, the average velocity, towards that of the instantaneous velocity, okay? And so here we have it. Simply apply this formula on the interval a to b, 2 to 2.01, do the simple little calculations, and we're finding that our average velocity over a very small interval of time, 1/100th of a second, is pushing 64 feet per second, which the calculus will show us is the instantaneous velocity at 2 seconds. And again, more on that will be discussed in the calculus. But for now, we want to know this computational proceedings in order to find the average rate of change, okay, over a given interval or over a very generalized interval, A to B, which was what we did right here. Okay, so that is all for this. Apologize, it get a little lengthy, but it's a lot of good stuff, okay, and we'll have some worksheets to help out the cause next class.